Hey guys, let's talk a little bit about the Lyapunov stability theory for linear time systems. So the basic setup is we have a system, linear time invariant system, a at x dot equals ax plus b. We have a Lyapunov function, x transpose px, right? We know that we're going to say that p is symmetric and it's positive definite. Okay. And now remember the necessary conditions for stability for that we need to show for the Lyapunov function to show that our system is asymptotically stable. We need that it's positive definite, which is guaranteed by this and this, right? We need that it's 0 when x is equal to 0. We're looking at the stability of the origin. And we need it to be negative definite. We need the derivative of it to be negative definite. Okay, so what does it mean when what is the derivative of v? So as I showed you before, x transpose xp dot plus x dot px is the derivative, which is equal to x transpose pa plus a transpose p, right? All right, and then now if we can show that if there exists a q, a negative q, where um, q is symmetric and positive definite, right? And so if there exists this q such that pa plus a transpose p is less than or equal to q, then we know that this guy comes over here on this side, right? Right. So we can further say that if q is greater than 0, we can say that the matrix A is what's called Hurwitz, which means that all the eigenvalues of A are negative, or the real components of them are negative. Or we can choose Q and solve the Lyapunov equation. PA plus A transpose P is equal to negative Q. So now we're picking Q and finding P. All right. All right, and so now we can look at a theorem, and I think I presented this theorem before. But this is one of the Lyapunov theorems. So a matrix A, Hurwitz, if and only if for any Q equal to Q transpose greater than 0, so positive definite, there exists a P positive symmetric positive definite that satisfies the Lyapunov equation. PA plus PA transpose P is equal to negative Q. And if A is Hurwitz, again, Hurwitz is right, where all the eigenvalues are negative. Then P is a unique solution. So that means that if A satisfies the Hurwitz properties of Hurwitz matrix, then there's only one P given a Q. Makes sense, right? So what's neat about this is we can actually use these equations for a nonlinear system to estimate, which may be difficult to estimate the region that would converge to the origin. For instance, a more complex nonlinear system. We can use hybrids, we can use Lyapunov functions to talk about the linearized case of a nonlinear system and estimate its basin of attraction, is what it's called. All right, so let's look at that. All right, so now for linearization, we looked at this abundantly in the class, right? So if x dot equals f of x, which is equal to a plus some other terms times x, and these other terms go to 0 as x goes to 0, okay? And then we can suppose that A is Hurwitz. Then there's a portion there's a portion of this system that would converge to 0, but maybe not on the global sense. All right, so next choose, since A is Hurwitz, we can choose Q is equal to Q transpose and solve the Lyapunov equation. What's the Lyapunov equation? Right, it's listed there at the top. PA plus A transpose plus P is equal to negative Q. Solve this for P. Okay. And then next we want to use the Lyapunov function V of x is equal to x transpose Px as the Lyapunov candidate for the nonlinear system. So for x dot is equal to f of x. Right? All right, so what's this look like? So V of x dot is equal to, taking the derivative of V, and we get x transpose P times f of x plus f transpose of x, P of x, is equal to x transpose P times A plus G of times x plus x transpose A transpose plus G transpose of x times P of x, or times P times x. Okay, so now this is going to be where our Lyapunov equation shows up here. P times x plus 2 x transpose P times G of x times x. And then this guy is equal to negative x transpose Q of times x plus, again, 2x transpose P G of x times x. All right. And so now we can start upper bounding this guy. Upper bound this guy by negative x transpose Q times x plus 2 times the norm of P, the matrix norm, times the norm of the function g times the norm of x squared. And now we can say that for any gamma greater than 0, there exists r greater than 0 such that the norm of g is upper bounded by gamma for all x greater than r. So we're looking at a radius of x about the origin, where g is less than some value gamma. All right, so now let's keep going. So we know that x transpose q of x is greater than the eigenvalues, the minimum eigenvalue of q times x squared, right? All right, so then this implies bidirectionally that x transpose of x is less than negative x transpose x is less than the minimum eigenvalue, negative minimum eigenvalue of q times the norm of x squared. Great. Makes sense. All right, now let's pick gamma less than this eigenvalue, minimum eigenvalue of q over 2 times the norm of p. Now, if this is true, if we can do this, then we get that for all x less than r, then we get that for all x less than r, v of x equals to x transpose p of x is the Lyapunov function, which means it satisfies all of the conditions of a Lyapunov function for x dot equal to f of x. So furthermore, what's neat about this is that, let me go over a little further, is that we can actually use p of x transpose to estimate the regions of attraction. All right, and so again, the region of attraction is the set of points about the equilibrium point that are guaranteed to converge to that equilibrium point. All right, so it's essentially, if I have, say, let's see if I can draw this, probably be pretty poor, but if I have this phase plane, x1, x2, and then I have functions, let's see what's the best way to do this. So there will be a region, there may be a region, if it's not a global stability result, that guarantees that the vectors of this phase plot, will all converge towards the origin in some way. Out here, it's not guaranteed that solutions will converge. We don't know what may happen out here. They could go out. They could orbit, but they don't. They will not converge. So this right here is what's called the basin of attraction. And so now what we can do, because we've linearized, we've approximated the nonlinear system using a linearized system, or let's see, go back to this A. So if we come down here, so if we have this function here, and we're approximating it using this A, which is we neglect the higher order terms when we linearize it, which is be these g of x terms. This is the same thing that's saying that the linear system acts similar to the nonlinear system around some region. Well, now we can actually characterize what that region might look like using Lyapunov theory. Okay, so that being said, oops, make sure, yep. All right, so we can actually use this Lyapunov function, since it's a Lyapunov function, to estimate a region or basin of attraction. All right, now how do we do this? Suppose v dot height of x is equal to 0 for all is less than 0 for all x, the norm of x less than some value r, and then we can take c equal to the minimum of t of x transpose px for x equal to r. This guy will be equal to the minimum eigenvalue of p times r. All right, so this means that a set of points x transpose p of x less than c is a subset of the set of points x of the norm of x less than r. Okay, so if I draw this pictorially, if I say that this radius is r, oh, can I make a circle? Yeah. Oops. Maybe. Ah, there we go. Okay, great. Figured out how to make a circle, you guys. Let's see if I can make a better circle. Close enough. All right, so I have a circle with radius r, and then we can have that there's a oval or some other shape that's contained in this. Oops. Like that. So this means that let's say that all trajectories starting in the set approach the origin as t tends to infinity. right? And then hence, this set of points, x transpose p of x less than c, is a subset of the region of attraction. And if you can read what I mean by subset, let's say an estimate. So that's pretty neat. That we can use this Lyapunov function to actually approximate the region of attraction for our nonlinear system using a linearized case. All right, next let's look at an example.